Hey, quiet, please. Hey, close the. Hey, at the back there. Close the door. Hey, close the door. Okay. All right. Now down, please. Is it you had a class before this? Huh? Just got here. Huh? Okay. Okay, before we start, let's just recap what we did last time. All right. Okay. So we started with the system. Okay, system is the real thing. All right, system could be a piece of fluid, a piece of solid, or something or other. All right. The control volume is an arbitrary box that we used as an analysis tool. All right, it has control surfaces, that's the surfaces on the control volume itself. All right, it can be stationary, moving, or deforming. Or normally in this unit we won't be deforming too much. We'll be maybe stationary and some are moving at constant speed. All right. Okay, and so we need a tool that converts mass continuity, which is basically mass doesn't get created or destroyed. We need a tool. We need to convert it into a control volume approach, and we did it this way. All right. Formally, it can be done in the Reynolds transport theorem. Those who like a lot of challenges, they can go and read this and think about it. All right, but this is a simplified way. All right, so for particular control volume, all right, particular box, all right, the mass inside the box can go up and down. It will not be conserved. Okay, mass is conserved in a system. All right, if a system is this battery, all right, this battery shouldn't get heavier or lighter on its own. Okay, if I track everything in this battery, I don't lose anything. All right, but for a control volume, it's just an arbitrary box, so it can get heavier or lighter if things go in. All right, so if things go in, mass enter, the box you expect to get heavier. If things start leaving, then the box will get lighter. This negative, this one will go down. All right, so let's take it on from there. Okay, so rate of change of mass in control volume is equal to rate of mass entering minus rate of mass leaving. Okay or not? All right, so if stuff enters at a rate of 1 kilogram per second, then your rate of change of mass in the control volume should be 1 kilogram per second. If things are leaving at 1 kilogram per second, then you expect this one to be reducing at 1 kilogram per second. That's why the negative here. Is that okay? All right. So, and this term, mass in the control volume is the density, all right, times the volume, and you integrate across the entire volume. All right. Okay. So integrate across the entire volume, or if this one you don't like because you haven't done for those who haven't done maths A. Okay. So this is sum of what? Sum of rho times volume times rho, the density at any position times the little volume at any position. All right, and you add it all up. That will be the total mass in the system. Okay, and we want the rate of change of that. Okay? Mass entering or mass leaving the control volume is equal to, well, density. Mass entering is this one is okay, equals this part here. If mass enters the control volume, all right, it's actually we can say it's the density times the volume metric flow rate. All right, this is the mass flow rate m dot. Okay, not? All right, mass flow rate like 1 kilogram every second. All right, if that density is, okay, so example, this could be 1 kilogram every second entering the control volume. All right, if the density is 1, be easy, okay, so 1 kilogram per meter cube, then we need 1 meter cube entering every second, 1 meter cube per second. All right, is that okay? So if we want 2, if this is 2, then either we have, if the density is still 1 kilogram per meter cube, then we need 2 meter cube per second. Or not? Entering. Is that okay? Alright? Okay, now this is the volumetric flow rate. Right, this is the volumetric flow rate. Right here, because we run out of space. If I want 2 kilograms per second entering, and the density is still the same, then I need 2 meter cube per second entering. Okay or not? Is that okay? Alright, and if I have, for a particular volumetric flow rate, if I have the volume, alright, it's actually the area times the length. Yes, lousy. Alright. Okay. So this is the area times the length. Alright now. So let's say for my control surface, the area that the thing is entering. Okay. So this is my control surface here. Alright. The part that is entering A is constant. Let's say for example, alright. So it enters at the constant area A. Alright. So if, example, if 2 meter cube per second needs to enter every second through an opening of say 0.5 meters, the area A equals to 0.5 meters. Alright. Then basically what this length must be 4 meters. 4 meters. So 4 meters times 0.5 give me 2 meters. Alright not? So the length. Okay? So basically 4 meters for a given area, or let's say 0.5 meters, 4 meters of this funny stuff, this block, this cube, ice block cube, has to enter every second to give me a 2 meter cube per second. Okay or not? Alright? So this volumetric flow rate is equal to the area times the velocity. Velocity 4 meter cube. So the area, in this case, is 0.5 meters. This length 4 meters. I need 4 meters entering every second. Okay, now that's why. So in this case, therefore, in this case, 2 meter cube per second is equal to area 0.5 meter squared times 4 meter per second. Units are all fine also. Okay, now. Alright. So you think of it that way. So by right, m dot is equal to rho AV. Rho, the density, multiplied by the area, multiplied by the velocity. Alright, which is equal to rho V dot. Same thing. Alright, area times velocity is equal to the volumetric flow rate. The volume entering every second. Area times length divided by the speed. Is that okay? Alright, so that's the easy part. Okay, so in here, I can write it in like that terms. Alright, but I'm missing one thing. Alright, Vector dot product, you know, right?